Okay, so people can hear me?
Yes, all good.
Excellent. Okay, well, thanks very much for having me. This is my second time trying to give a talk on Zoom, and it is quite interesting. Actually, it's very awkward because I can't see you. So I actually don't know what the reaction is. So, and I was told that I'll be giving a talk to a wide range of students. So I'll try to make it as understandable as possible. So today I'm going to talk about the status of photovoltaics, which is a fancy word for solar cells, and the role of research and development. So I'll talk about what are the driving forces for the increased uptake for solar photovoltaics, and where's the opportunities for research and some of the new hot research topics and the projects that students can be involved in. Can we squeeze more out of the sun? And yeah, we'll find out. Okay, so we'll just do a quick run through of how solar cell works. Solar cell usually is made of semiconductor material, meaning that at room temperature, it doesn't conduct electricity. But when it's given enough energy, it will conduct electricity. So imagine a semiconductor that's got electrons that are not free to move about when it's at a low energy state. And when it's given enough energy, what happens is the electron will jump onto the conduction band and becomes conductive. So you can see that the electron gets jumped onto the conduction band and it becomes, it's able to move about. So it leaves behind a hole. And this hole, if this electron, now these electrons are able to move about. So if this electron moves to here, effectively the hole moves over here. And if the electron keeps moving, and then the hole effectively moves. So you can imagine, see the movement of the hole, you can actually represent that hole as a positive charge. So that's a sort of an idea that you need to grasp. When we talk about solar cells, you have a positive charge and a negative charge, which we always talk about electron hole pairs. So there's this thing about the band gap. So when I'll just stop that. When there's two ways of exciting a semiconductor, is thermally exciting it or using light energy. And the energy needs to be higher than the band gap for the electrons to move up to the from the valence band to the conduction band. Oh, so this one we have seen already. Okay, so the absorption of light. So what happens is you have light shining onto the solar cell, and you have three scenarios. One is the energy of the photon is smaller than the band gap. So do you know what happens? Nothing happens. And there's another case where the energy of the photon is larger than the band gap. Then the electrons will be able to jump from the valence band to the conduction band and make the material conductive. And the third case is you have a perfect match where the energy of the photon is same as the band gap energy, and therefore you have a conducting material. So this is just an illustration. The photon energy is below the band gap and it goes straight through the semiconductor. Then you have the photon energy larger than the band gap, and you have the electrons jumping onto the conduction band. It becomes conductive, but you see this excess energy. It doesn't get used for electrical energy, and therefore it gets wasted as heat. And you have a case where the photon energy is the same as the band gap and no heat is wasted. Okay, so now you got the concept of electrons, holes, band gap. Then how do you direct the electrons to move in a way that you want it to? So we have, for example, we have p-n junction where we dope the material to have excess electrons or excess holes. And when you bring the two materials together, you form a p-n junction and it forms an electric field. And if you provide the correct bias, you're able to make the electrons to flow in a certain way. So one way of thinking about it is like a valve for the water to flow through. You want to have a valve in a certain way that you know For example, if you have a valve in a right way and you rely on the gravity to push the water down, and if you turn it upside down, then the water won't pass through. So same in here. So if you apply a positive bias, a forward bias to the cell, where you have the positive on the P side and the negative on the N side, then you're able to get the electrons to go the way you want it, and therefore you're able to generate electricity. Whereas if you put it under reverse bias, you basically like turn the valve upside down, you're actually stopping the water from flowing. Okay, so then there's this concept of IV curve, which is very important. So when we look at solar cell papers in the literature and publications, they always show an IV curve. So the IV curve is sort of like the merit of how good the solar cell is. So the squarer of the IV curve, the better, the higher the voltage, the better, the higher the current, the better. So I didn't mention that. Actually, I'll just describe this first. So the solar cell is like a diode, as I have explained. So it's like a one-way valve where the electrons will go through in one way. So a diode curve will look like that. So meaning that once you have a voltage that overcomes the built-in voltage of the diode, you will have a rapid flow of current. So as soon as it overcomes that voltage, it'll flow like that. And then you have the sun. So the sun is basically a current source on the circuit diagram. So you have the current flowing the right way, it will flow through the diode. So it goes like that. Now you can notice that the current is negative here. So what it's saying is this element, the circuit element, is generating electricity. One thing I didn't mention is the band gap. If you remember in the previous slides, we talked about the band gap. So the larger the band gap, it means the higher energy photon is required to excite that material into a semiconductor. So the higher the band gap, it means the lower the short circuit current will be. And if it's a lower the band gap, you'll get higher the short circuit current, which is this number here. Hang on. So this number there. So I don't know whether you can see my mouse, it's over there. So anyway, in a lot of literature, you'll see the IV curve. So also, it's also proportional to the amount of sunlight that shines onto the cell. So if it's partially shaded, you'll see that the short circuit current will be also low. So in the literature, you will see that the IV curve is actually turned upside down, and that's just our convention of reporting the cell results. So perhaps people just like seeing IV curves in the first quadrant, and therefore we just put it like that. But it doesn't mean the solar cell is using energy. It still means the solar cell is generating electricity. Okay, so you got the idea of how solar cell works. So the incumbent technology is silicon. So how do you make a silicon solar module? So you start from sand or quartzite, and it's very abundant. So you just purify the sand using high temperature processes into metallurgical grade silicon, which is also used for steel making. And after metallurgical silicon grade silicon, you can turn it into either solar grade or semiconductor grade. Even for silicon grade is 99.999 purity. So you sort of melt the silicon into this crucible, and the whole idea is to push all the impurities onto the ends of the crucible. So you will have certain impurities on the top and then certain impurities on the bottom, and you end up with this ingot. And then you slice this ingot into what we call wafers. So it's a piece of silicon wafer, and then you can dope it using phosphorus or boron to make it P-type or N-type to form that PN junction. So after you have the PN junction is there to separate the charges. So once you have electrons and hole generated in the silicon wafer or in the silicon cell. It gets separated, so it will go the way you want it to be. But really, to collect the charges, you need the metals and the electrodes to collect them. So, so you end up with a silicon cell with metal contacts, and you interconnect them in series for the typical solar module. So you have 72 cells, for example, building up to a high DC voltage. And then you have some diodes there as well. If you have shading of the modules, then you have 1/3 of it still working instead of the whole lot not working. And you sandwich them between polymer layers, glass on the front, and a polymer on the back. And there you have it. You have a module that can withstand rain, sun, hail, wind. Yeah, and this is how a typical solar module look like. So they are mass produced and has been made very cheap over the years. Okay, so why silicon? As I've said, they're very abundant. They're non-toxic. It's a proven technology. So in the early days of manufacturing, a lot of the processes were adapted from the semiconductor industry. They're durable and they take up, at the moment, they take up 90% of the market. So if you look at the cost reduction over the years, so you can see cost in 2011, the manufacturing cost of module, manufacturing cost of cell, manufacturing cost of wafer, and the manufacturing cost of producing that polysilicon, you know, the purification process that I've shown. You can see that in 2011 cost $4 per watt. And over the years, so only in 9 years or 10 years, has reduced to around 40 cents per watt. So it's 10 times reduction. And that's because it's driven by, there was a large uptake of solar modules in Germany in the 2000s. So it's driven by government policy. So suddenly people have to make solar modules very fast, very quickly, and in a large volume. So that drove a lot of manufacturing industry happening in China. So back then they didn't know how to, you know, make those solar cells, let alone glass. So they imported a lot of glass from Australia, in fact. But over the years, they've worked out how to do things. So they worked out all the way from glass manufacturing down to how to purify silicon. So, and for them to make money, they have to increase the production. So they have to build really, really, really large mass production manufacturing factories to sort of beat the other competitors, and that really drives the cost down. So now the only big players now in China. So a lot of the plants, in fact, closed down in Europe and North America because of the drive to expand. And in fact, there are lots of cheap silicon modules, good quality, around because of that expansion. So once you expand, you can't stop, and you can't have a production line that runs, you know, 80% at a time. Has to run it at 100% at a time. So anyhow, then the question is, why not just stay with silicon? You know, we're doing well, you know, photovoltaics cheap, everybody is putting it on their roof. 50% in some of the suburbs in Australia, 50% of the rooftops have got solar modules, and on average the nation's got 15% of rooftop photovoltaics. So why? Well, that's because silicon has got one single band gap of 1.1 eV, so it's good at absorbing light near the infrared. It also absorbs light above the infrared, but if you remember, when you have photon with an energy higher than the band gap, it does get absorbed, but what happens? It generates heat. So a lot of the energy gets wasted. And yes, you can absorb high photon energy, but the voltage of the solar cell is still very low. So for example, for silicon cell, the output voltage of the cell is around 0.6 V. So you can have higher bandgap materials. For example, if you have a bandgap of 1.5 eV, and it's a direct bandgap material, the output voltage is around 1 eV, so it gives you a higher voltage. So what can you do with these different kinds of materials? you can actually stack them. So what you can do is you can stack the, hang on, yep. So you can stack a higher bandgap material on top of a lower bandgap material. So for example, if you have a blue cell that is very good at absorbing blue sunlight, they'll absorb it. And the with photons with energy lower than the blue, what happens? It goes straight through. So it just funnels through and it doesn't get wasted. So we're picked up by the cells on the bottom, and this is what we call tandem solar cells. So on this graph, it shows the theoretical efficiency of a single junction cell as well as tandem solar cells. So you can see a single junction cell, if you have a material with a band gap of around 1.1 something eV or 1.3 EV, it will give you a theoretical efficiency of around 33%. But if you stack two materials together, and if you have the top band gap of around 1.6 EV and then a bottom cell with a band gap of around 0.9, you can see the theoretical efficiency jumps by 10%. So you can see the advantage of stacking different materials together with different band gaps to make the most of the sunlight. And you can see with this 3-junction tandem, you get more than 50%. And as you go up more, you have more stacks, the increase becomes marginal. So you have increased complexity, but a lot of work, but not a lot of gain. Okay, so what are the materials that you can use that are alternative to silicon, as well as you can use it for tandem? So you can use group 3,5 material, which are those ones in the periodic table. So they have been used. They're used mostly in the space applications, and tandem 3,5 tandems are being used for space applications as well. And if you increase the concentration on the sunlight on the cell, meaning you're running at a high concentrations, you get very high efficiency, around 40-something%. However, they're very expensive. So they deposit it using very expensive equipment. The size is usually very small. The production is in small volume, and they're 50 times more expensive than silicon. So it was $4 per watt. Now we're talking about, $200 per watt, thousands of dollars per square meter. But they're good for space application because for space, the cost of bringing stuff up sometimes is more expensive than the cost of the material what you want to bring up. So there also another alternative is perovskites, which a lot of you would have heard already. So what's so good about this material is it's got very good electronic properties. It's got very good optical absorption, and we can make it thin. So we can make it 500 times thinner than silicon, and we can process it at low temperature. So in silicon, the purification process, all those doping process and all of that takes 1,000 degrees to make, whereas in this case, it's only 100 degrees to 200 degrees. And it can be processed by solutions. So all these examples I show you are basically fabricated using the precursors of the materials, dissolve in a solvent, and you can spread it, you can print it, you can spray it, you can even blow dry it onto the film. And you can see you can also make it different colors by tuning the composition in there for the band gap. So materials with different band gaps will have different appearances as well. So perovskites got this crystal structure. So A is the cation. It can be organic or inorganic. So the world record efficient solar cells use a hybrid version where the cation, it's got the organic. And then the B site is where the metal is. So it can be lead or tin. And then the purple is the iodide or bromide chlorine. So is hybrid, organic, inorganic, metal, halide, perovskite. So this is the perovskite that has been sort of capturing people's imagination and attention, research attention. Thousands of people have been working on this material, using these materials for solar cell applications and LED Okay, so you can see because it's thin, it's very lightweight. So it's got a very high weight to power ratio, or they call it specific power. And therefore, you can see that it's very good for things that are moving, for example, vehicles or in the space applications. And because it's thin, it can be put on a flexible substrates and for flexible applications. So you can imagine it being used for buildings as well. So the material has been the highest performing PV material in the last 10 years. So you can see the efficiency doubles in 7 years. It's highly possible that a 27% efficient cell will come out very soon. And there's a diversity in the chemical composition. So if you vary the organic ion into different types of organic cations, or you place the lead with tin, or you can mix it, you can have 50% tin, 50% lead, or you can mix the iodide and the bromide, you can have 50% or 15% usually, then you can actually tune the band gap. So it makes it a very versatile material. And that means you can use it for tandem. So you can see the optical absorption is very good. Absorption coefficient is very good. It has low recombination, non-radiative recombination. It's got high potential for high efficiency. So again, I have talked about that you can spray it, you can print it, you can just blow it by just put a blob on your substrate and blow it. You can evaporate it as well. So you can have the powder, the perovskite powder, and you can heat it up and it will deposit onto the substrate that you want. And again, it's not very high temperature. We're talking about hundreds of degrees instead of thousands of degrees. So this is a typical cell structure. It doesn't, so it's deposited onto what we call a superstrate, because in this case, the substrate or the thing that the solar cell is deposited on is also facing light. So it's called superstrate. It doesn't have to be glass. It could be plastic. It could be flexible glass. Then you usually have a transparent conductive oxide. Could be ITO, indium tin oxide, or fluorine doped tin oxide, FTO. Then if you remember electrons and holes, so you can have a hole blocking layer or hole transport layer, and the position of these two can be swapped. So hole blocking layer may be titanium dioxide or tin oxide. Then you have the perovskite layer, and you can see it's only 0.5 micron. You only need a little bit for it to absorb sunlight. Then it's capped by the opposite transport layer. So if this is an electron transport layer, then this will be a hole transport layer, HTM. And then it will be finished off by electrode. If it's an opaque cell, then it will be a metal, or if it's a transparent cell, it will be a transparent conductive oxide of some sort. So you can see that the whole cell combined, the thickness of the whole cell is actually thinner than the substrate itself. And when we look at the cost analysis, it's exactly the same. It's very, very cheap to make the solar cell. It's actually the cost of the substrate that is a large proportion of the total cost. So some of the interesting research projects that we have here, we have single junction cell, double junction tandem, and triple junction tandem. So I'll go through all these and some of the projects that you can be involved. Okay, so with the tandem, there are different ways of making tandem solar cells. So either you can directly deposit the high band gap cell onto the bottom band gap cell with some sort of intermediate layer. And this is what we call the monolithic tandem. Or you can stack two cells together, just mechanically stack them, put one on top of each other, and then you can have some sort of medium there just to reduce the optical loss. And we call it the mechanically stacked, and it's 4-terminal because you have a pair of wires coming out from each cell. Or you can even use some optical element to, for example, a filter to reflect the light, for example, in this case is a low energy light onto a low bandgap cell, and then high energy light onto a high bandgap cell. So this, in terms of integration, is the easiest, but you can have optical losses through these optical elements, and also you just have all these extra wires dangling coming out. But on the left-hand side, the integration is the hardest, but it's the most elegant in terms of the wiring that's coming out. You only need to worry one pair of wires. So in my lab, we're interested in the monolithic integration of tandem cells. And as you can see, when you stack layers with different refractive index, you run into a problem of constructive and deconstructive interference. And the worst case is you don't want the reflected light to come out to sort of interfere with each other in phase, and then you get really large reflection of what they call Fresnel reflection. So what we do is we stimulate different kinds of cell structure, a tandem cell structure, to see what happens. So there are 3 different cell designs in this case. You have the silicon cell on the bottom, and then the perovskite, so the titanium dioxide is the electron transport layer, and you have the spirometad, which has got a really, really long chemical name, so we call it spirometad or spiro for the whole transport layer. So all 3 cells have similar perovskite and silicon cell structure, except the very top, which is the transparent conductive layer. So it's either a stack of very, very thin gold that lets light in, also conduct electricity, or ITO on this side, or graphene, which conducts electricity, and if you have it thin enough, it will let light through. So what we do is we just run some optical simulation to see what happens. So we look at this cell on the left, and the optical losses and gains, the graph is right in the middle. So the red layer represents the reflection of the entire cell, so the total reflection, and you can see sort of the interference patterns coming up. And the gold layer, you can see this is the parasitic absorption, meaning the absorption that goes into the gold instead of going into the solar cell. So you can see it's very large. So the gold is very absorptive. And what's get left over to the cell is the orange and also the green. So here is saying the cell is able to absorb this much amount of light, perovskite, and then the silicon cell is able to absorb this much amount of light. And if you move to the right-hand side, you can see that the ITO is performing better. So there's not much absorption there. You can hardly see anything. You can see a little bit. And a lot of light gets through to the perovskite cell. So it's managed to produce 16 milliamps per square centimeter, and so is the silicon cell. And you can see in all 3 cases, the spiro is very absorptive of the short wavelength, so around the UV range, which is annoying. And it's sitting on the very top of the cell. So like, you know, people have skin cancer because the skin absorbs the UV light on the surface very well. So what do you do? Well, you can replace the spiro and replace it with something that is less absorptive. Or one of my students is very clever. He said, well, why don't we get around it? So what he did was he put a down converter. So he infused some phosphorus into a PDMS layer and put it on top of the solar cell. And this layer converts UV light into green light. So the spiro's got nothing to absorb. It's got no UV light to absorb, and it lets green light pass straight through. So that way the perovskite is able to enjoy the high energy wavelengths. And he's managed to find some really very efficient down converter. Also, to improve the light management of the cell, we decided to texture the PDMS layer and also texture the back. So when we texture the surface of the solar cell, it allows the sunlight to be coupled into the cell instead of being reflected. So, you know, if you have a flat like mirror image, you will get quite a lot of sunlight being reflected. So you look at the cell, it looks like a mirror. Whereas if you texture it, you will get as much light into the cell and get it to bounce around as well. So when you have light being bounced around the solar cell, it increases the chance of the light being absorbed. Also, you can see, you know, in theory, we look at titanium dioxide, but in practice, we have got to use tin oxide. And the reason is titanium dioxide, you know, it requires 500 degrees for processing. So it's not very good. It's expensive and it's bad for the silicon cell on the bottom. So we replace it with the tin oxide as well. And yeah, looks easy. We get 23%. But of course, in reality, there's a lot of research being put in. For example, we have to make sure the doping of the P material, I'll just go back, of the P material here is optimized so that it will do a good job of separating an electron and holes and get the electrons to go up, the holes to go up and electrons to go down. Also, the interface, the tin oxide interface is very tricky. We want it really thin to make it deposit onto the silicon cell. We've got to make sure the silicon cell is wettable, and that means we will have a little bit of silicon dioxide on the cell, and then we worry about the barrier created by the silicon dioxide. So yeah, so a lot of analysis, characterization, and simulations is involved to make absolutely sure we optimize the layers, the very thin layers as well as the thick layers. So if I show you the cell design again, you can see that the perovskite cell is right on top of the silicon cell. So that means the two cells are connected in series. So basic circuit theory, if you have two circuit elements connected in series in the circuit, then the current has to be equal and the voltage adds. So if you have two resistors, for example, in parallel, then the current adds and voltage is equal. So anyway, in this case, the two cells, the current have to match. So however much current going through the perovskite has to match however much current that is going through the silicon. So what it means is you want a perovskite to be thick enough to absorb enough sunlight to produce enough current to match the silicon. You don't want it to be too thin, but you don't want it to be too thick either, because it absorbs a lot of sunlight, but it gets wasted anyway because the silicon is limiting the current. So yeah, so here it's showing that, you know, we've got to optimize the thickness of the perovskite cell to optimize the efficiency of the tandem. So you can see you've got to have the right thickness. Anyway, the mouse is not listening to me. Okay, so what can new students be involved? Well, we've got a new project where we're very ambitious. We're looking at 3-junction tandem. So we're looking at stacking 2 perovskite cells onto a silicon cell, and we've got some preliminary results. So this is a preliminary design of our cell without disclosing too much detail. And you can see there's like more than 10 layers in there, and you can imagine the optical design will be interesting. So any enthusiastic students who want to join my group, you'll be given the task of optimizing the layers, the thickness of each layer to optimize the optical absorption. So this is just a graph to remind you why we want to do 3-junction, because of the efficiency potential. Also, we're looking at upscaling to a larger area. So remember, current is proportional to sunlight, and the amount of sunlight onto your solar cell is proportional to the area of your cell. So the larger your cell, the more sun that hits the cell, and therefore the higher the current. And the higher the current means more resistance as well if you don't change the way you design your metal. So the more the current is, the larger amount of metal or electrode that you need to conduct the electricity. So, but then you don't want a big fat wire on top of your cell that shades half of the sunlight. So you need to design your metal grid clever enough to control the what I call the electron traffic. So you can see on the left-hand side, this is just an old boring grid. When you have current generated from one side, it just go to, you know, the roads that is immediately available, and you see a big voltage drop, meaning a big loss. Whereas if you design it in a clever way where the electrons got a lot of rows to travel on, then you have a much smaller voltage drop and therefore lower electrical losses. So these are very interesting projects where students can be involved in. Okay, so the second problem of perovskite, or a major problem of perovskite, well, the first problem we sort of, it's a solvable problem anyway. Such a good material will give us good efficiency. But the material are quite sensitive. So sensitive to moisture, sensitive to thermal, sensitive to light. And that's put it in a bad situation when you want to put it on top of silicon. So silicon's performance warranty is 25 to 30 years. So that means in 30 years time, you still have a working solar module, but maybe with 17% degradation. So if you have a 100-watt panel, you still have, for example, 80 watt left after 30 years. It's got a piece of thick glass on the front, so it's got a product warranty of 15 years. So what we want to do is we want to develop perovskite to be durable against moisture, thermal, and light. Okay, so to do that, we've got to understand. So don't worry about the right-hand side. Look at the left-hand side first. To make it stable, we've got to understand how it degrades first. And to understand how it degrades, we want to find out what comes out when it degrades. So what we do is we deliberately torture the cell while it's in a bottle, and then we collect the gases that come out, which are the degradation products. And then we put it through this measurement called the gas chromatography mass spectrometry, which is a good technique for testing drug cheats, for analyzing soil samples on Mars, or looking at any chemical warfares, detection of any explosives. So we thought, yeah, that would be a good way of looking at perovskite cells. So in fact, you would have thought that, 2 to 2, people can put 2 to 2 with 1, but not a lot of people thought that you can use GCMS to look at perovskite cells. So as soon as we published the paper in Science, someone from UQ wrote to me, we use GCMS every day. How come we never thought of using it for perovskite cells? Anyway, so what we did was we tortured the perovskite materials at high temperature to make it outgas, and then we identify the products. So the GC separates the mixture into different components, and the MS, depending on the mass of the compound, we're able to identify what they are. So you have all these signature products, and then you can find out what happens, what the thermal decompositions are like. Then you use the signature products to evaluate the effectiveness of your encapsulation. So if you protect the solar cell and you protect it well, and you put it through the GCMS, you shouldn't be able to see those signature products. But if it's not protected well, you will be able to see those signature products. So in this case, we use a very low cost way of encapsulating the cell using materials, for example, PIB, polyisobutylene, or polyolefin. That's used for laminating 2 pieces of glass in the industry. And we use different ways of protecting the cell. Either we use the polymer as a blanket to completely cover the cell, or use it as edge sealant. So just to put it on the edge to seal the 2 pieces of glass together. And in this case, we rely on the FTO to conduct the current out, rather than using a physical metal wire for the current to conduct out. So anyway, we found the blanket approach is the best. So we look at unprotected cells and also protected cells, and we can see that the protected ones have very, very low outgassing. So you can't see those signature products coming out. So what we found is this encapsulation, people think encapsulation is to protect the cell from external elements so that moisture can't go in. But in fact, it's actually protecting the cells from moisture as well as stopping the thermal decomposition. So what happens is, if you have this blanket approach, the gas can't come out. It's got no way to come out. Whereas if you use the edge sealant, it can come out to the void and therefore drives decomposition reactions. So yeah, so that's sort of one of the major finding we found that is not known in the computer, and we managed to confirm that's the bifunctional, the two functions that is played by the encapsulation to stop things from going in and to stop the decomposition reactions from happening, because it's airtight encapsulation. So we look at, perhaps we can look at polymer-free glass encapsulation. So, so this is in partnership with David McKenzie and School of Physics, because they've got quite a lot of experience with glass. And we look at whether we can use water glass or another bonding for low temperature bonding, and we can do it without the polymer. So projects you can be involved in is look at the merit of these bonding techniques, look at the bond strings, carry out some shear stress tests, and also look at the hermeticity by using this thing called the spinning rotor gauge. So basically, the more hermetic the joint is, the tighter the joint is, this unit will be able to hold vacuum, and this ball will be able to spin very fast. So it's almost, the hermeticity is proportional to the speed of the spinning ball. Okay, so we talked about the durability of cells in land. Then we can look at the perovskite cells in space. So why? Because of the high specific power. So it's got a very good power to weight ratio. And people have been looking at its resistance to high energy electrons and protons. And surprisingly, perovskites perform very well. And it's because, partly, I think, because it's a soft materials. So it's exposed to radiation and then it self-heals. Also in space, there's no moisture. So we've got, you know, one big enemy out of the way. And we just need to worry about the other things like shocks, atomic oxygen, other kinds of radiation, plasma. And thermal cycles, we know it worked really well. I forgot to mention that. So here, what we did was, apart from looking at the decomposition products that are coming out, we actually torture the cells under damp heat and humidity free. So damp heat is 85 degrees Celsius and 85% relative humidity. We want to accelerate test them, meaning that we don't have 25 years to wait for perovskite cell to last. We want to accelerate test them to see if they can withstand high cycles of torturing and long hours of damp and heat environment. So yeah, these comply with the IEC standards that is used for the current photovoltaic products. So we can see that this encapsulation strategy that we propose is working really well, extremely well. So this is actually the record durability of perovskite cells ever reported. With humidity freeze, we cycle them through -40 to +85 degrees at high humidity as well. So if you have any moisture being trapped into the cell, it will crystallize and break the joints of the cell. And we found that our methods work really well, and that we didn't have problems after long cycles of humidity freeze. So yeah, thermal cycles is doing well. So we've got a very talented student for our special project this year, and he subjected perovskite cells to plasma generated by the dielectric barrier discharge. And we found that the cells are actually behaving as well as the silicon cell. So that's very encouraging. And more exciting projects for you guys to be involved in, looking at the durability of cells in space and what designs work and what designs don't work, and the packaging strategies. What sort of substrate do we want? We want it as lightweight as possible, but then also radiation resistant. Also, it will be interesting to be able to integrate the cells with electronics suitable for satellite applications. It will be exciting if we can launch the satellite with perovskite cells on them. So we also look at perovskite for BIPV application. How am I going with time, Arjul?
I think you're doing well. Maybe another 5 minutes, so we have more time for discussion.
Yeah, no problem. So I'll just go through this really quickly. So we're also looking at perovskite cells on buildings, for example, in between two pieces of glass. So why do we care, where we put the cell? Because we don't want solar cells to heat up. When they heat up, they don't perform as well. But we also, want to look at how it will affect the performance of the glazing, double glazing, especially if it's for thermal insulating glazing, either with air or vacuum in between. So do we put the cell on this side or do we put the cell on this side? And of course, someone say, well, of course, if you don't want it to be hot, you don't want to put it here because it gets hot and the heat got nowhere to go. So is it? So we actually did the calculation to, sort of to verify our intuition. So anyway, this is a whole bunch of elements that we need to take care of for the heat transfer calculation. We look at the different scenarios of the cells in hot and cold weather, perovskite versus silicon, double glazing with air or vacuum. And we found that to calculate the temperature, we need the emittance values. So the emittance values is quite trivial to measure if we decide to measure it using the integrating sphere. Then you got to integrate all the values, all the angles. But there's another way of doing it is actually use transient calorimetry. So basically measuring the change in temperature, and then through the change in temperature, we can work out the total hemispherical emittance using this Stefan-Boltzmann law. And I won't go through in the details because then we have more time for question and answer time. So we have this set up, and using this principle, we're able to calculate the emittance of the solar cell using the known reference, for example, copper or a black material with known emittance, measure the temperature change curve, and we can work out the emittance of the cells, and we plug that into the formula in the heat transfer equations, and we managed to find out the temperature of the solar cell as well as the temperature of the glass, whether it's on the outdoor pane or indoor pane. So what have we found? Well, we found that in hot weather, perovskite cells run well on the internal glass. So the temperature is not affected at all, and that's because it's got low emittance. Whereas for silicon cell, it's better to mount it on the external, so on this side of the glass, because they've got higher emittance. In cold weather, it's best to mount the cells onto the external glass if you care about the temperature of the perovskite cell, of the solar cells. And if you want to use the solar cells for indoor heating, you can actually mount them on the internal glass. So these are the findings that we sort of never expected. We also run some tests to see if we change the emittance of the solar cell, it will have an effect on the thermal performance. So it's a very interesting area where maybe we can do emittance engineering for thermal management. Okay, so what sort of BIPV building integrated photovoltaics project you can be involved in? Okay, well, we've done some back of an envelope calculation for the Sydney Nano Hub. Imagine it's covered in solar glass, solar window, what happens? So our back of an envelope calculation say we can save $10,000 a year. Well, is it? So it'll be interesting if students can use the measure data to relate the energy received on each aspect of a building. So this is my office building with a data locker that locked the solar insulation on the inside of the glass. And we did a calculation and that's what we arrived at. But it will be good to do a better job at that and then take into account of the incident angle, reflectivity from the, maybe from the courtyard or from the other buildings and, shading, seasonal variations, etc. Okay, so Archil, how much time have I got?
Yeah, you can go ahead. So it's almost on the expense of discussion time.
Okay. So anyway, just to inspire you, I think we're doing great work. We're doing our part for the environment, reducing the carbon dioxide emission. I remember this really struck me when the Australian journalist asked this professor, what is the difference between 2 degrees and 4 degrees Celsius in terms of global warming? And he said the difference is human civilization. So if we do experience a 4 degrees temperature rise, basically 90% of the population will be made extinct, and the 10% will be living in Tasmania. Renewable energy is growing. So since 2013, we're adding more renewable energy than coal, natural gas, and oil combined. The rate of increasing renewables is steady, and in terms of PV, it's been increasing by 25% a year until last year around 16%. But if you look at the number of jobs, the proportion of photovoltaics in renewable is less than 10%. But the amount of jobs that go into PV within the renewable energy sector is 1/3, 33%. So I looked at our students that have no trouble finding a job, and I think it is a great area to work in because you're really truly doing something for the world. There's still a lot of people without electricity. So in this photo, this lady in the rat cap is me 15 years ago. And we took a group of undergraduate students to Nepal installing, such a small solar system for the medical clinic, and it's still useful. That trip was only just to provide lighting, and then the next trip is to provide a fridge for the medicine. And that medical clinic served 20,000 people in the region. They had no electricity, no running water before we came. So, yeah, renewable energy is really doing a lot of good. And for a lot of people without access to electricity, photovoltaics has been providing a very good solution. Children can read at home at night and they can go to school. So it's got a flow-on social benefits as well. So my call to action is get involved. And that's it for my talk.
Thank you very much, Anita. This is a very, very informative talk, and with the research with a lot of very important applications. So we can open now the Q&A session. And well, I would like to encourage first students to ask questions. So there are two ways of doing that. Either you raise a hand and we'll look at the chat, or if you don't know how to do that, just unmute your mic and talk. Yes, please, Claire.
Hi, Anita. Thanks for the talk. I was just wondering, I've been reading a little bit about, hearing about these 3D printed solar panels going around. I think University of Newcastle's doing some work on them. Yeah. How does that compare to the sort of work you're doing?
Yeah, so they are OPV, organic materials. So OPV, I believe it's OPV. So there are two types of OPV. One is dye-sensitized solar cell. One is the polymer base. And they've been sort of been around for a while, and the efficiency has been increasing steadily, but it's not rising as fast as the perovskites. So sort of a lot of people from the OPV area has moved into perovskites, but now there's a revived interest in OPV again, for example, with the non-fullerene type polymer cells. They're able to get efficiency higher, 17%. So the University of Newcastle group, they focus on the roll-to-roll printing, and the rationale is if you can print them like you print newspaper, then you'll be able to do mass volume at a very sort of low-cost way of making solar cells. But the importance is still efficiency is quite important, with those kind of materials, it's very hard to look for them to be used for tandem, because if you look at the calculation for materials to be useful for tandem, you really need them to be 20%, because you don't want to stack a low efficient cell on a very good silicon cell. Basically, you're just wasting the light. Yeah, so it's just, I would say, a bit different focus. They were thinking of maybe low efficiency and low production cost, will be able to justify for a market for it. But I myself believe that you really do need the efficiency because installation is costly. You can't afford to install low efficient panels.
Brilliant, thanks.
Right, other questions? Yes, please, you can unmute your microphone and ask questions, please.
Okay, well, if that's the case, I'll fire one off to Anita. Oh, someone else there already? No, sorry, just an echo at my end. Anita, I was just interested, you were talking about the resilience through damp cycle of the cells and the fact that the perovskites, if I pronounced that properly, deteriorate under heat, and the typical Australian solar flux of around 1 kilowatt per square metre is going to inevitably make them run quite hot. I was wondering if in your GC and mass spectrometry, if the loss of chemistry that comes out from the cells actually results in a change in the band gap structure and a change in the efficiency curves that your hopefully double or triple tandem will have.
When it degrades, it degrades into a completely different material. So usually it just end up being just lead iodide that looks yellow, and it's got a band gap of 3 eV or something, and it's not useful. So when it degrades, it's actually not useful. So it's sort of like either 1 or 0 result, rather than it will change the composition. But it does, if you remember the halide, you can have a mixed halide perovskite. So you can have a mixture of iodide and bromide, and those halides segregate. So sometimes when it's unstable and light can actually get the iodide or bromide to segregate out, and they segregate into the grain boundaries. So yeah, so sometimes if you do some luminescence measurements, you can actually see grain boundaries light up with different color. Yeah, so that's very interesting. So if you're doing tandem, you're in a bit of a trouble because you deliberately tune the band gap for it to have tune the composition to have certain band gap, and yeah, they're not evenly distributed. But if you can engineering in such a way that the high band gap material segregates out onto the grain boundaries, it actually provides a defect passivation effect. So what we found is with perovskite, some of the bad things that happen, we can engineer it to do the good things for us.
Interesting choice that it would do that, I suppose, if you're almost lucky and the grain boundaries are an adequate size, they might form grazing incidents to keep sending some of the light to the lower cells. But I suppose that will impact, as you were saying before, about getting even energy delivery from each part of the double or triple.
Yeah, so we were mucking around with the inorganic version as well. So we found that the cesium metal halide perovskite is very stable thermally because there's no organic stuff. So there's no outgassing. But the phase is not stable. So we turn it into our advantage. So what one of my students did was he replaced some of the lead with strontium, and it makes, then the material is even more unstable, but unstable in a good way. And he managed to segregate out some of the strontium onto the surface of the cell. And then the strontium is with a little bit of a higher band, so the band gap is slightly higher. So he ended up with having a bit of higher band gap material on the surface. And they also managed to passivate the defects as well. So yeah, it's a very interesting material. People just, you always see things that you don't expect, and then people try to engineer it for their own advantage. Another thing with unstable phases is you can make it into a smart window solar cell. So when the phase is not stable, it becomes transparent. And then it lets light in. So it's a good solar window. So if you can engineer that at night, then it lets light in, you can see outside, or during the day. So for some privacy reason, you want it to be opaque and absorb sunlight, then you can turn it into a smart window. So one of the Nature or Science paper actually make use of the instability of cesium metal halide perovskite for that purpose. Peter, you muted.
Multiple computers. Another basically valve, like you were talking about, water running one way and not running the other way. So an optical valve based on the amount of energy deposited per cubic volume. Yeah, interesting choice. I suppose that would tie definitely into Chenk's work and hit that part of the team in physics.
Mm-hmm.
I have a question.
Okay.
So, are perovskite cells like being used commercially yet, or is it still like very much in research right now?
Yeah, so there are around 5 startups around the world. Used to be in each continent, so there used to be one in Australia as well, which was it was a dye solar cell startup and then turned into perovskite, so they jumped ship.
Okay.
Yeah, so they're looking into upscaling. So there are quite big demonstrations in China where they use. So remember, I show you our cells use the metal electrodes. They use carbon electrodes, and when they use carbon electrodes, the cells are a lot more stable, but the efficiency is not as high. But anyway, they managed to do some large area production as demonstration projects. There's also another startup in China, and they keep breaking their own world records in terms of making large area modules. There are 2 startups in America spinning out from Stanford and another university, MIT, I think. I don't remember now, actually. And there used to be one in Australia. So yes, so it seems like there are people who are willing to invest in this technology. When is going to be mass produced? I don't know. It's like how long is a piece of string? But so many people are working on this technology, it's very hard to put a timeline on it. So meaning it could be more optimistic than we think.
Okay, and was like the main issue the durability issue that you were talking about before, or?
Yes. So we managed to solve the thermal problem and the humidity problem, but we haven't managed to. Well, we don't know whether we have managed to solve the light plus thermal plus humidity. So all 3 together will be interesting. If we can't solve all 3 together, we put them in Arizona or somewhere in space.
All right. Okay. Thank you.
You're welcome.
Are there any other questions to Anita? Oh, let me check the chat. Nothing in the chat. No hands, no unmuted microphones. That means we have to thank Anita again and close today's.
Question.
Sorry, Jan.
A question for Anita, Arju.
Yes, go ahead, please.
Anita.
Yes.
How long is a piece of string? Can you give us an estimate of when you think there'll be a significant market for perovskite cells? When I say significant, better than 2%.
It's hard to say. I guess my answer is if it doesn't happen soon enough, then I wonder whether it's whether it's a technology, but it's hard. Like for example, with the polymer OBV, people lost interest, and then suddenly someone found something. You know, the non-fullerene type is so we've got to wait for accidents to happen. You know, sometimes huge breakthroughs is done by accidents.
Sometimes it's very hard to plan the research.
I would love to see it mass produced. I would love to see startups in Australia happening.
It's up to you, Anita, you and your team.
No problem.
Good luck.
Ian. Any further discussion or questions? All right, then thank you, Anita, again. And let us close this session today. Tomorrow we'll be discussing about dark stuff in the universe. So it's a change of gears, but yes, please at 3 p.m. please join us as well. Thank you, Anita, again. Thanks.
Thank you. Thanks for having me.